Alright, so hopefully the algebra matrices went really well for you guys. So now we have 3 lessons left. This is Introduction to Matrices, kind of a different form of it and why we actually use matrices. We're talking about matrix notation again and Gaussian elimination. So order we've already talked about. Order, remember, of a matrix is rows by columns. So your order of this matrix A is A2 by 3. Now the value of A13 means you go to row 1, column 13. So row 1, column 13, column 3, sorry. Row 1, column 3. So I'm in row 1, column 3. That number is a 1. So with the first row over to column 3, there's a number there. A21 means row 2, column 1. So row 2, column 1 would be 5. Now if you get something like A32, that would be row 3, column 2. There is no number there, so you would just say not possible. So whenever they ask you for the order, and they're going to say, hey, now what's the value of this? It's always row by column, always. All right? An augmented matrix, so the major application of matrices are used in solving linear systems of equations. One strategy for solving a system with matrices will require us to translate a system to a augmented matrix. So to construct the augmented matrix, here's what you do. You want to make sure your columns are lined up with x's, y's, and the numbers, all right, in your system. And so this first one is, and so here's how you do it. I construct this matrix by taking the coefficients of the numbers. So 3 is the coefficient, -7, and then you draw a line, a straight line here, to construct your augmented matrix that represents our equal sign, -4, and then I end my matrix. You do the same thing for the bottom, so -1, 4, and then 9. And that is called the augmented matrix of a system of equations. So then they'll give you something like B, which is kind of tough because you have to simplify it before you can do anything. So I'm going to divide both these by 2. What I like to do is I always like to rewrite the equations to make sure they're in the correct order. So it needs to go x, y, z equals a number. So this first one's 2x divided by 2, which will give me 1x. -6y divided by 2 gives me -3y. If you notice, the z is on the other side of the equal sign, so I'm going to add it to the other side, and it's going to say plus z equals 3. The next one is out of order, but you can rewrite it in the correct order. -x plus 5y plus z equals 12. And then lastly, you have this one where the z is on the wrong side and the 2 is on the wrong side. So you're going to get x plus 3y minus 2z equals 2 because I added the 2 to the other side and I subtracted the 2z to the other side. So now it's in the correct order. I can make my augmented matrix. So 1, -3, 1. I draw my straight line to make an equal sign, 3. And then I end my matrix. And you do the same thing for the next equation. -1, 5, 1, 12, 1, 3, -2, and 2. Okay? So that is how you construct an augmented matrix. So I want you to pause the video and I want you to try this one right here. So construct the augmented matrix for this linear system. So again, I always like to rewrite the equations. So hopefully that's what you did when you paused the video. So 4/5 x, this is going to be plus 11/5, but I don't want that on that side. I'm going to subtract it to the other side. I'm going to subtract the 9/6y to the other side as well. So when you do that, that becomes -3/2y. I need to simplify it. Minus 1/6z. If the z is on top, you can make it a fraction. Equals -11/5. So that first fraction is kind of a tough one. On the first equation. Next one I have to distribute. So I'm going to get an x. I have -6y, but I'm going to subtract the y over, so it's going to be -7y. Minus 42z equals 6. And then the bottom equation, it should have been 2x plus 9y minus 7z equals -4. So then we're going to construct our matrix. We're going to say 4/5, -3/2, -1/6. Draw our line to make the equal sign, -11/5. and I get 1, -7, -42, and 6, and then I get 2, 9, -7, -4. Okay? So augmented matrix, you have to know how to convert them, a system, to an augmented matrix in order to solve these problems. So then that leads into Gaussian elimination. So translate the following augmented matrix back into a system form and solve the system. So if we do this, you'll notice it goes x, y, z again. So I'm going to say 1x plus 2y minus 2z equals 11. Notice there's 0 x's, so I'm not going to write an x. Y minus z equals 3, and then z equals -1. So when you know what z is, you can use that to solve the system. I'm going to plug it in here. So y minus a -1 equals 3. That's y plus 1 equals 3. So I get y equals 2. So then the last one, I know z and y, so I can plug it in. So I'm going to have x plus 2 times 2 minus 2 times -1 equals 11. So x plus 4 plus 2 equals 11. X plus 6 equals 11. Subtract 6. X is 5. So now you have solved for the system. You know it's 5, 2, -1. So Gaussian elimination requires something called a row echelon form. So when we do a row echelon form, the first non-zero entry in each row is 1. We call this a leading 1. Every entry below a leading 1 is 0, and each leading 1 appears further to the right than the leading ones in the row above it. So all rows consisting entirely of zeros, if there are any, appear at the bottom. So what that means is, like, say I have a 3 by 3. You essentially normally want it to look like this, and then whatever the numbers are, because that means you've solved for x, y, and z. So notice the 1s are diagonals. So that's what we call row echelon form. In order to get to row echelon form, you have to do elementary row operations. Really, it's not too bad. What you're doing here is you're going to take a row and you're going to multiply it, or you're going to change it, whatever it may be. So this first one, you see how it says row 1 and then it has a double arrow with row 2? That means we're going to switch row 1 and row 2. So we're going to take row 1, which is the 0, 2, -3, and we're going to write it in row 2 spot. And then we're going to take row 2 and we're going to write it in row 1 spot. So 1, -1, and 4 is going to go on the top. So that's what you can do with elementary row operations. That's one operation you can do. You can switch the rows. Because look at this. It gives us the 1 in the top left, which is what we want, and a 0 in the bottom left, below it. So then you have 1/4 row 1. So I can take a whole row and I can multiply it by a number, a fraction, a whole number, doesn't matter. So this one we're dividing by 4. If I multiply by 1/4, that's the same as dividing by 4. So I'm going to say same as dividing by 4. But notice I'm only doing it to row 1. So that's going to become 1, -3, and 2. Row 2 is not going to change because I didn't change anything in row 2. I just changed row 1. Next one, and this one's the important one. All right, if you're going to take a row and multiply it and then add it to another row, the row that you are multiplying, or the row that's first, so row 1, does not change in this case. So this first one, whichever row is first, does not change. So what I always do is I just copy it down, and then I go back and I do the operation. So now I'm going to take row 1 times -2. So I always write those numbers above it, -2, 4, and 10. So I multiply every number by -2, and then I'm going to add it to row 2. So I'm going to take -2 plus 2, which is going to give me 0. 4 plus 3, which is going to give me 7. And then 10 plus 1, which is going to give me 11. This one I'm taking row 2 plus row 1, so row 2 is not going to change. All right, so now I'm going to add it to row 1. So when I do that, I get 1, 0, and 1. And that's what you want. So that's some elementary row operations. So I'm going to give you an example of how we use that to help us solve a problem. All right, so first thing is you want to make an augmented matrix. So I'm going to have 4, -6, negative 8, 6, negative 76, and 66. So now the thing about this is there's a lot of ways to go about it. Your goal, though, is to get a 1 here first, and then zeros below it. So the first thing that I'm going to do is I'm going to take row 1. I'm going to divide it by 4. So I'm going to take 1/4 times row 1. So what that does is that gives me 1, negative 2, and negative 19. Notice row 2 did not change. But now I look at row 2 and I'm thinking, oh, I can divide all those by 6. So I'm going to take 1/6 of row 2. Just makes it a little bit easier. So I'm going to get 1, negative 2, negative 19, because row 1's not going to change. The bottom's going to become negative 1, 1, and 6. Sorry, not 6, 11. All right? So then I'm looking at this and it's like, all right, I have a 1 here now. That's what we want. How can I get a 0 here? Well, I can take row 1, because that's the one I don't want to change, and add it to row 2 to get a 0 there. So when you do that, remember, row 1's not going to change, so it's going to become 1, negative 2, negative 19 still. Row 2 is going to become 0, because 1 plus negative 1 is 0. Negative 2 plus 1 is negative 1. Negative 19 plus 11 is negative 8. So now if you notice, all I need to do is get a 1 here, and then I am done. So I'm going to multiply row 2 by a negative 1. So what that does is this right here solves for y. So I know y is equal to 8 because there's 0 x's, but there's 1 y. So when you know that, you can write the top equation, and you can solve it using that information. So x minus 16 equals negative 19. I'm going to add 16. X equals negative 3. So my answer to this problem would be negative 3, 8. So that's how we use Gaussian elimination to solve the problem. Our goal is to get a 1 in the top left and then zeros below it, and then we go to the diagonal from there. So now I'm going to get into one that's a little bit bigger. All right. So this will probably be the last one. When I write this in an augmented matrix form, I have 1, 4, there are 0 z's, so I'm going to write a 0 there, and then 13. And remember, my equal sign is represented by a straight line. So 0 x's, 1, negative 6, negative 9, negative 4, negative 5, 1, negative 17. So the nice thing about this is there's already a 1 here, there's already a 0 here, but I got to get a 0 here. So how am I going to do that? Well, I'm going to take 4 times row 1 and add it to row 3. So row 1 and row 2 do not change. Now what I do when I multiply is I always write the row that I'm multiplying below it. I just write the numbers that I would get. And then I add it separately. Alright, so when you do that, you're going to get 0 here, which is what you want. 11 here. 1 here. And when you add those, you should end up getting, let's see, 52 minus 17 would be 35. Okay. So we're good. We have all zeros below it. We have a 1 on the top left. So now we go to the next row. I want a 1 here, but I want a 0 here. So how am I going to get a 0 there? Well, I'm going to take row 2 by negative 11 and add it to row 3. So when I do that, row 1's still not going to change because I didn't do anything to it. Row 2 is the one I'm changing, so that's not going to change either. And then row 3, so after I multiply everything by negative 11, get those numbers, I'm going to add it to row 3. So I'm going to get 0, 0, 67, and then 134 when you add it together. Okay? Now, we're almost done. That's a 1, that's a 1. I need this to be a 1. So if you look at it, I'm going to take row 3 and divide it by 67, which is the same as saying 1 over 67 times row 3. Because 67 goes into 134. So the other rows do not change, but row 3 is going to become this. So now I know that z is 2. If you know z, then you can solve for the second equation. That's y minus 6z equals negative 9. So y is 3. And now that you know that, I can plug that into the top equation to solve for that one. So x plus 4y equals 13. So x plus 12 equals 13. Subtract 12. X is 1. So now my answer is going to be 1, 3, 2. So now you have x, y, and z. Okay? So that is how you use Gaussian elimination, and that is what the certify is over. Your homework is going to be 10.2. If you guys have any questions, please let me know.